In this lesson, we will look at a mechanical ice protection system, as used on the ATR-72 shown here. A mechanical system, using pneumatically inflated boots, may be employed on the wing and tail leading edges of certain types of piston engine and some modern turbopropeller aircraft. This type of system is used for de-icing. It removes ice that has already formed on the surface. It is switched on when there is an ice buildup of between 0.5 and 1.5 centimeters, depending on aircraft type. The de-icing boots, or overshoes, which are fixed to the leading edges of the surfaces to be protected, consist of layers of natural rubber and rubberized fabric, between which are fitted flat inflatable tubes closed at one end. The tubes are also made of rubberized fabric. In some boots, the tubes are so arranged that when the boots are in a position on a wing or tail leading edge, the tubes run along the leading edge. In others, they run across at 90 degrees to the leading edge. The boots may be attached to a leading edge either by screw fasteners or by cementing them directly to the inboard portion of the leading edge, where the wings are thickest. The tubes in the boot sections are inflated with air from the aircraft's compressed air system. This air may come from the pressure side of an engine-driven vacuum pump, from a high-pressure reservoir, or, in the case of some types of turbopropeller aircraft, from the engine compressor. The inflation weakens the bond between the ice and the boot surfaces, causing the ice to break away. At the end of an inflation stage of the operating sequence, and whenever the system is switched off, the air is sucked from the boots to hold them flush with the leading edge. The suction may be produced by a vacuum pump or by Venturi action. This inflation and deflation cycle is repeated during the period the system is in operation. When the system is switched off, suction is applied continually to all tubes of the boot sections to hold the sections flat against the leading edges, thus minimizing aerodynamic drag. This type of system has two drawbacks. Firstly, the boots disturb the airflow over the leading edge, increasing drag. And secondly, they are quite expensive to maintain, as the boots wear out relatively quickly and they are easily damaged and eroded. The de-ice boots are pulsated in a set cycle, the frequency of which can be varied by a frequency selector to cater for light or heavy icing conditions. To reduce the volume of pressurizing air required, the boots are usually divided into groups. For instance, Group 1 may be the port and starboard wing outboard boots. Group 2, the port and starboard wing inboard boots. And Group 3, the fin and tailplane boots. When the system is switched on, the boots will inflate and deflate in sequence. First Group 1, then Group 2, and finally Group 3. At the end of the cycle, there will be a time delay, which can be varied by the pilot, depending on the severity of the icing before the cycle starts again. The controls and indicators required for the operation of the system vary from aircraft to aircraft. In the basic arrangement, there will be a main on-off switch and a selector to allow the pilot to select the time between cycles, depending on the severity of the icing. There may also be pressure and vacuum gauges or indicating lights to confirm system operation. That is the end of the lesson. You should now understand that a mechanical system using pneumatically inflated boots is often used on modern turbopropeller aircraft. You should know that it can only be used for de-icing purposes. You should also know that the two disadvantages of this type of system are that it is expensive to maintain and that it causes an increase in drag.